Physics Penguin.
Welcome to Physics Penguin's Guide to Forces and Energy. Today we're going to look at the link between forces acting on an object causing them to move and the energy it takes to make that object move. There is a worksheet of questions to try that will check that you understand this topic. It's linked in the video description. Let's talk about work. Work is a word that means energy transferred in physics. You will often see questions ask you to calculate work done. This really means work out how much energy is being transferred. Don't forget the units. Force is always measured in newtons. Energy or work is measured in joules. Okay, so let's have a think about how much energy depends on force. Time for a thought experiment. Cue strange music. Imagine you are out with a baby. The baby is in a pram. She likes to be out and will complain if the walk is not long enough. It can be tiring pushing the pram because you are applying the force. So what determines how much energy this walk will need? Well, if the baby is heavy and the pram is hard to push, it will take more energy. If the baby is demanding a longer walk, that also needs more energy. If the baby is heavy and demanding, that will take an awful lot of energy. This thought experiment shows that energy, work done, depends upon the force applied and also the distance the force makes the object move. We can turn this into a simple formula. Work done equals force times distance moved in the direction of the force. W equals F times S. Yeah, I know. S for direction again. I don't make the rules. So W is work done, energy in joules. F equals force in newtons, and S is distance in meters. There are a couple of interesting points here. Firstly, work is force in newtons times distance in meters, so work in joules could also be measured in Newton meters. The second point is about direction. Time for another thought experiment. Imagine that you work in a factory making big crates in the Antarctic. When a crate is made, you have to lift it up and slide it over to another crate and place it on top. If the ice is lovely and slippy, it will take no force to slide on at all. How much work is done lifting the crate? Well, it's just the weight of the crate multiplied by the height you lift it. If you put it on a pile close by or far away, it makes no difference. Only the distance moved up matters because the weight was pushing down and that was what we fought against. Be really careful that you only include the distance moved in the direction of the force, not just the total distance. There are some examples of this on the worksheet. Finally, let's talk about what this energy is doing. In the example of lifting a box, our energy went into the box. When we lifted it, we gave it stored gravitational potential energy. The box will keep that energy until some stupid walrus or something comes along and knocks the box off when the energy gets released. So what kind of energy comes out? Well, kinetic energy to start because the box is moving. When it hits the ice and stops moving, its energy probably turns into heat and sound. Maybe it doesn't actually explode, What were you keeping in those crates? Okay, now it's time to have a go at the worksheet. Use the link in the video description. Pause the video and we will go over your answers when you're done. Okay, welcome back. Let's have a look at the answers to the worksheet. Question 1 is our old favourite, a table of calculations. Our formula this week is pretty simple. Work done, energy, is force times distance moved in the direction of the force, or F equals W times S. So the work done in the table will be the force times distance, and the distance is 5 metres each time. So something times 5 is 30 in line 1. Well, that must be 6. 6 times 5 is 30. In the second line, something times 5 is 15. So that'll be 3. In the third line, something times 5 is 25. Well, 5 5s are 25, so it's 5 newtons. And in the last line, something times 5 is 250. So that is 50 newtons. Okay, well, question 2 is interesting. We have to compare stopping a lorry and a car. Why is it easier to stop a car? Well, it must be to do with forces, and it is easier to change the speed of something with less mass. The question isn't really about weight, be careful of that. Just imagine pushing a car. You could probably push it slowly down a flat road with some effort. I doubt you could push a truck. So our answer is just that it takes more force to stop a lorry at the same speed because it is bigger and it has more mass. The second bit seems odd. What happens to the temperature of the brakes? Well, this is a good question because you've started thinking about forces, but this is about energy. If you apply a force to an object over a distance, that is doing work. You are transferring energy away from the kinetic energy of the vehicle and into something else. What forms of energy are common for getting rid of excess energy? Well, sound maybe, possibly light in special circumstances, but the number one choice is thermal energy, heat. Brake pads get hot. In the old days, they could just be blocks of wood, and these things could even catch fire. All the kinetic energy we lose is going into those pads, so they are very important bits of engineering. Then there is a question about escape lanes. Why have a sand road on downhill parts of steep roads? Well, if you're in a big lorry and going quite fast and have a problem with your brakes on one of these hills, you may not be able to get around corners and could cause a crash. The emergency lanes have a couple of useful features, obviously just in an emergency. First, they're usually flatter than the rest of the road, making it a bit easier for the vehicle to slow down. Secondly, the sand is pretty hard for wheeled vehicles to travel through, so even if you have complete brake failure, the extra friction with deep sand should slow you down fairly safely. And question 3 is kind of the opposite to the last question. Why does an ice skater travel so easily? Well, we need to use work equals force times distance, and we know that work should be low, but distance is large. That means that the force it takes to make somebody move in ice skates must be really low. So, why? Well, look at this picture of the blades. They are sharp, and all your weight is on them. They actually cut into the ice and cause the ice under the sharp parts to melt. You are then gliding on a smooth, sharp metal blade on top of a bead of water over smooth ice. The water refreezes as soon as your weight moves on, but there is very little friction with the ice at all. This means our force F can be tiny, but a small amount of energy or work will still let us move a long way. You could trust me on this, I'm a penguin. That seems to be everything for now, so if you found this useful, check out the rest of the playlist. Please subscribe to be notified of the next video going up. Until next time, this is Physics Penguin saying ta-ta.
Physics Penguin.